Hello, Mr. LaRusso here, and welcome back to SPH3U, Grade 11 University Prep Physics. Today we're going to be taking a look at Newton's three laws. In the last video, we looked at an introduction into dynamics, and specifically we talked about the difference between dynamics and kinematics, what forces were, the normal force, free body diagrams, and the net force. We also took a look at what is defined as weight versus mass. We're going to continue with these topics, but specifically look at Newton's three laws that govern motion. Now, Sir Isaac Newton is arguably the most famous figure in physics, and for good reason. Sir Isaac Newton came up with some remarkable intuitions that were quite counterintuitive for his time. So let's take a look at the three laws, and we're going to start off specifically with something called the first law. Every object maintains a state of rest or uniform motion in a straight line unless acted upon by an unbalanced external force. Okay, so what does that mean in plain language? Essentially this: the natural state for all objects is to either be at rest or moving in a straight line, and specifically a straight line, at a constant speed. This is actually somewhat counterintuitive, and this explains why, up until Newton's time, we held the belief that the ancient Greeks put forward is that constant motion does require a constant force. And when you think about every single day life, that actually does make a lot of sense from that perspective. So imagine this is a floor and we have a box. This box is not going to move until we apply a forward force, at which point the box will then start to migrate forward. But the moment that we remove that forward force, we know that the box, again, when it eventually will come back to rest. This is the most intuitive understanding of motion. But Sir Isaac Newton argued that that actually isn't the correct viewpoint, which is a remarkable achievement because based on all the everyday activity that we would experience, this is exactly how we see it. You have to push an object and keep pushing it, otherwise it comes to a stop. But Sir Isaac Newton said, no. The actual default is constant motion and it should go at a straight line forever and ever. Well, how did he come up with this somewhat counterintuitive viewpoint? Well, it started off with an experiment, which then turned into a thought experiment. So let's just imagine essentially a half pipe. So we have this curved track. And Sir Isaac Newton noticed that if you release a marble from a specific height, the marble will roll and will stop when it reaches approximately the same height on the other side. And what was fascinating about this is that if the height started lower, it would reach almost the same height, but slightly lower on the other side. So then he argued, well, why is this the case? Does it have to do with the distance or does it have to do with the height? Because here, although I did not draw it that well, there's symmetry here. Well, what if we had a non-symmetrical track? So what if it was steeper on one side and more gradual on the other? Well, when you conducted this experiment, surprisingly, the object tried to reach the same height. It didn't matter that the distance here was longer. It didn't make a difference. What seemed to be important was the initial height and relative to the final height. So then he speculated and asked the following question. Well, what would happen if our ramp system moved off to infinity? Well, according to his argument, during this part, it would accelerate. But then when it reached the bottom here, it would move forward at a constant speed forever, essentially, unless it ran into another obstacle. Now, of course, that doesn't happen. We know that eventually this object is going to come to a stop. And that's where Sir Isaac Newton defined the reason for this as a separate force known as the force of friction, which is interesting because the concept of friction as a specific force didn't exist until Sir Isaac Newton described it in that fashion. So he went against 2,000 years of accepted understanding of motion to come up with this somewhat radical idea. And he's right, because the behavior of planets and satellites cannot be explained in any other way effectively. Now, as a little side note, there are some improvements in astrophysics thanks to Einstein, but that's for a topic for another day. So effectively, the first law describes the behavior of objects, all objects, under the influence or absence of forces. And what's it related to? Well, the Newton's first law is also called the law of inertia, and inertia is related to an object's mass, and it is defined as an object's resistance to a change in motion. So objects tend to either want to stay put or they want to keep going in straight lines. They don't want to turn. That's generally not the default. It's either at rest or straight line. And then it requires forces to intervene on that behavior. Well, living in Canada, we experience what happens when people don't respect Newton's first law, especially during the first snowfall. In normal conditions, if we're driving our vehicle and we are driving forward and we hit a curved section of road, normally it is no problem to follow the path of the roadway. Now, what allows us to follow the path of the roadway is the force of friction between the road and our tires that's allowing us to make that curve. However, in winter, this force of friction is diminished. And as a result, the car can't make the curve and ends up sliding off into the ditch or into a snowbank. So if we were to modify the law for a Canadian winter, all cars maintain a state of rest or uniform motion in a straight line unless acted upon by an unbalanced external snowbank. Newton's second law. So Newton's second law specifically talks about the rate of acceleration of an object. And it's defined as follows. An object's acceleration is proportional to the applied unbalanced force and inversely proportional to the object's mass. So what does that actually mean? Well, if we were to look at it as a proportionality, what it's saying is that the acceleration is directly proportional to the net force applied to it and indirectly proportional to the object's mass. And this is actually one of the more intuitive concepts. The harder you push something, the faster it should speed up, or the faster it should slow down. And the other next big idea is that the heavier the object is, the harder it is to get it to speed up, and the harder it is to get it to slow down. This explains why transport trucks and trains, even though they have extremely powerful motors, which can produce massive amounts of F net, their acceleration is comparatively lower to other vehicles, and that has to do with the fact that their masses are so much higher. In car terms, we often refer to that to the power to weight ratio. Motorcycles have huge power to weight ratios. Lots of power, very little mass. Passenger cars, not quite as good as motorcycles in terms of that ratio, but still, relatively speaking, they have a lot of force compared to their mass. But then you get things like big trucks and trains where the mass is proportionally much larger compared to the engine. So even though the engine overall is still quite strong and quite massive, it's dominated by the amount of mass that those vehicles possess. So let's take a look at the formula. And this is the main formula that we use in Newton's second law. Now, we already talked about the net force. The net force, if you recall from earlier, F net is defined as the sum of all the forces acting on the object. But F net is also equal to the mass times the acceleration. What you should probably see is that these two F nets are actually the same, and that's what's going to get us further along solving problems involving forces. So let's take a look at an example. Let's find the net force acting on a 10 kilogram object that is accelerating at 5 meters per second squared south. All right, so working in GRFS, we have a mass of 10 kilograms, acceleration of 5 meters per second squared south. Fairly straightforward. F net is equal to ma, which is equal to 10 times negative 5. Now, why is it negative 5? It is because it is going south. So F net equals negative 50. Converting this negative 50 into a direction, negative in this case means south. Example number 2. We're looking to find the acceleration of a 15 kilogram object that is experiencing a net force of 30 newtons to the right. So our mass is 15 kilograms. Our net force is 30 newtons to the right. Now, since it is to the right, we consider right to be positive. So to find the acceleration, we need to rearrange our equation to isolate for acceleration. To isolate for acceleration, we have to move the mass, and we move the mass through division. Substituting our values in, we end up getting A is equal to 2 meters per second squared, or 2 meters per second squared to the right. Finally, Newton's third law. Newton's third law is defined as follows. Every action has an equal and opposite reaction. You may have heard this before, but there are some very specific ideas that need to be clarified. When we say every action has an equal and opposite reaction, this always refers to two separate objects. So this means that if one object exerts a force on a second object, that second object exerts the exact same force back on the first object. Key difference? In the opposite direction. So consider when you give someone a high five. When you give someone a high five, you're applying a force on their hand, but their hand is applying an equal and opposite force back to you. So if you give them an aggressive high five, your hand's going to sting too. Another less pleasant example is stubbing your toe. If you've ever carelessly walked into a room not looking where you're going and you kick a table, you are well aware that the table is going to hit you back with an equal and opposite force. The harder you hit that table, the worse it feels on you. Other examples or evidence of the third law is in any sport that involves a battery. And what do I mean by a battery is anything that you strike an object with. Hence in baseball, we have a baseball bat. And as you can see, the word bat comes from battery. So when a baseball comes flying at you, you hit it with the bat, you can actually feel the feedback of the Newton's third law happening in the bat itself. That feeling of when it connects. Same thing happens with a hockey stick, tennis racket. Basically anything involves where you're hitting a projectile with a battery. That feedback that we feel is a direct result of Newton's third law. So some examples. If you punch a wall, the wall will punch you straight back. And if you hit it hard enough, you'll end up going to the hospital with a broken hand because the walls fight back with an equal and opposite force. If you kick a table, the table kicks you right back again. Here's another example. That's the example where you stub your toe of Newton's third law. Turning on a high-pressure water hose. When you turn on a high-pressure water hose, the actual hose will start to fly aggressively around. And that's as a result of the water shooting out the end. The hose is pushing the water out, but the water is pushing the hose back. Something similar happens if you ever fire off a shotgun. When you fire off a shotgun is going to recoil. That recoiling is a result of the third law. The gun is applying a force on the bullet to move forward. The bullet is applying a force on the gun to move backwards. And literally, any and all motion is a result of the third law. You cannot have motion without it. Example, walking. If you are walking forward, in order for you to walk forward, you actually apply a force backwards on the ground. You push the ground back. It is the ground pushing you as a third law in the forward direction that causes you to move forward. So technically speaking, every time you walk, you actually push the earth back a little bit. However, that motion is so undetectable, and the reason being is that the earth is so much heavier than you and I that it barely moves under the influence of the force that you apply. Similar to this idea is if you're in a parachute and you are falling towards the earth. Technically speaking, not only are you skydiving and falling towards the earth is actually technically falling towards you a little bit too. The earth is pulling you down, you're pulling the earth up. Again, the earth is so massive though, and as a result of the second law, it barely registers any acceleration whatsoever. And for all intents and purposes, it is you that is accelerating and the planet is effectively standing very, very still. Rowing or paddling. You apply a force backwards on the water. That's what causes the boat or the canoe to move in the forward direction. We intuitively know this, but you don't realize it until you think about it, that what actually causes the boat to go forward is you pushing on the water backwards. Flight, the exact same thing. The propellers in the plane are basically fans on steroids. So when the propellers start flying and twisting, they're pushing the air backwards. But the air is applying an equal and opposite force forward, which causes the plane to move forward. Jet engines work in the exact same way, and rocket engines do the exact same thing. With rockets, it is the chemical reaction of the rocket fuel and the oxygen within it that turns that solid rocket fuel into a high pressure, high temperature gas. Those hot gases escape out the rear of the engine. So the engine is applying a force backwards on those gases, and the gases are applying a force forward on the rocket, causing it to move forward. So let's take a look at an example of the third law. And we're going to simplify it by ignoring the effects of friction. So we have two students, Andrew and Eric, and they're standing on perfectly smooth ice. All right, when we say perfectly smooth ice, that's physics code for ignore friction. Technically, there is friction there, but we're just going to ignore it. So let's take a look at the situation. Eric pushes Andrew with a force of 42 newtons to the right. Now, here's the key thing. It's Eric on Andrew that we're talking about. And that is force of 42 newtons to the right. But the way we represent this is the force of E on A, because that's the force that Eric applies on Andrew. Now let's take a look at these two individuals. Eric and Andrew have different masses, 70 kilograms and 60 kilograms respectively. Well, what does respectively mean? Well, that means the first name goes with the first number. So that would be Eric's mass, and that would be Andrew's mass. So the first thing we're asked to find is the reaction force that Andrew applies against Eric. Then we're asked to find Andrew's acceleration, then Eric's acceleration. So to solve these problems, we really have to be really particular about the subscripts. So again, let's take a look what we got here. ME stands for mass of Eric, 70 kilograms. MA stands for the mass of Andrew, which is 60 kilograms. And then FE on A is the force of Eric on Andrew, and then that is 42 newtons to the right. So what we're looking for, though, is we're looking for the force of Andrew on Eric. Do you notice how the variables are flipped around? Well, let's take a look at what that means. So to answer the first question, to find FA on E, this is how it is argued. Since Eric pushes Andrew with a force of 42 newtons to the right, therefore Andrew produces a reaction force of 42 newtons to the left. Or, and this is how I would prefer you to argue it on a test, for example, the three dots means since. Since FA on E is equal to negative FE on A, and what this is this says every action has an equal and opposite reaction. Every action has an equal and opposite reaction. And that is Newton's third law. And we know that FA E on A, Eric on Andrew, is 40 newtons to the right. Therefore, FA on E is equal to 42 newtons to the left. And the reason why that is, folks, and remember, is negative in physics just means direction. So negative, in this case, represents to the left. Next, we're asked to find the acceleration acting on Andrew. So what this means is we have to focus specifically on what Andrew is feeling. All right, so we're going to take a look at the free body diagram of Andrew, and Andrew alone. So we have the mass of Andrew. And Andrew's experiencing the following forces. Andrew's weight, the normal force acting on Andrew, and the force of Eric on Andrew. And when we take a look at this, Eric is pushing Andrew to the right. So what we know is this. We know that the net force acting on Andrew is equal to the sum of all the forces acting on Andrew. And that is FE on A, FNA, and FGA. However, these two forces, the normal and gravity, they cancel each other out because they are equal but opposite to each other. So they ultimately have no effect. So then we're left with F net A is equal to positive FE on A. And the positive means to the right. Rearranging, substituting in, we get acceleration due to Andrew is equal to positive 0.7 or 0.7 meters per second squared to the right. Finally, we're asked to find the acceleration of Eric. So when we look at the acceleration of Eric, we have to focus on what Eric feels. So Eric is feeling the following forces. Eric's normal force, Eric's weight, and the force of Andrew on Eric. And that is the third law that we're looking at right here. These two forces are equal and opposite to each other, but here's the key. They are applied to different objects. So these two forces are happening on separate objects, specifically Eric and Andrew. So in Eric's case, we have a similar thing happening here. The normal force and the force of gravity cancel each other out. And the reason why is that neither of them are floating or sinking. There is no motion in the y-axis. It is all happening in the x-axis. So Eric is experiencing a force to the left. And since he's experiencing a force to the left, when we drop the vector notation, that's when the negative sign comes in. Rearranging and isolating for the acceleration due to Eric, we get negative 42 over 70, and that's equal to negative 0.6 meters per second squared, or 0.6 meters per second squared to the left. Now let's compare these results. Notice that the rate of Andrew's acceleration is larger than the rate of Eric's acceleration. And that makes sense because Andrew's mass is lighter. So since Andrew's mass is lighter, the same force will cause him to accelerate at a greater rate. And since Eric's mass is larger, his rate of acceleration is diminished because of it. And that, ladies and gentlemen, are the three laws in